Now that we've found the normal as well as the tangent vector, what's left to do is to find the binormal vector. And the way to do that would be to take the cross product of the normal and the tangent vector, and that would give us the binormal vector. Once we have that, what we need to do is we'll need to use the normal and the binormal vectors as axes for which our cross-sectional circles will lie on the path of the spiral. So before we go ahead and code that, let's take a look at what the equation of circle looks like. So what we have is, if we have a circle with a center here and radius r, the equation of this circle becomes r sine of theta, r cosine of theta, written in a matrix form of 2 dimensions. Now, another way to write this would be, for a 2-dimensional circle, the equation of a circle is simply the linear combination of these 2 vectors, because this would equal to r sine of theta plus r cosine of theta. So that's the equation of circle. Now, if we want to plot a 2-dimensional circle in 3-dimensional plane, all we really need to do is add another element, another dimension on the basis vector, so 0, 0. So this would simply give us a 2-dimensional circle in a 3-dimensional plane. Now, what the interesting thing that we can do here is that we can replace this column with the normal vector and this column with the binormal vector, and a linear combination of this with this matrix would give us the circle at a certain position. So let's go ahead and code that in Python. So first of all, we had the tangent and normal vector. Let's just make sure that we can store them in variables. So tangent normal would be equal to our phasor and curve. So what this would do is this function, taking our curve function as an input, would give us the tangent and normal, and those would be stored in these 2 different variables. So there we go. If we want to take a look at the coordinates of a tangent at, say, time t equals 0, all we really need to do is put 0, and there you go, those are the coordinates. Alright, so now what we want to do is we want to create a function that would give us the surface of the hose that we want to make. So let's define that as surf. Now, the first thing we want to do here is find out what our binormal is going to be. And we already know that this is a simple cross product of the tangent and the normal vector. So that would be jnp dot cross of the tangent vector and the normal vector. So let's define our tangent and normal vectors as well. Our tangent vector is simply tangent t, and normal vector is simply normal of t. So this gives us our binormal vector. And what we want this to return is the actual coordinate of where the circle should be. So return, again, this is the linear combination that we talked about last time. So first of all, we need to make a matrix that has the tangent vector, the normal vector and the binormal vector in 2 different columns. The way to do that would be just use jnp stack, and it looks like this: jnp dot stack, and we'll supply the 2 vectors, that's n and b, and we want the axis to be 1 because we want this to be based on columns. There's that, and we do a matrix multiplication, which is symbolized by this symbol, matrix multiplication with our actual array of r sine theta and r cosine of theta. So that would be jnp dot array square brackets. So we have r times np dot sine of theta and r times np dot cosine of theta. We'll have to supply the values of r and theta as well, so we're going to do that outside the function. According to our main problem statement, we know that r has to be 0.5 and theta is simply any value from 0 to 2 pi because those are all of the angles within a circle. So that would be theta equals jnp dot linspace from 0 to 2 times np dot pi, and we'll make 18 different values for theta. And yeah, so this function should technically be able to give us the coordinates of where our circle should be lying on. So one last thing that's left to do is like this statement right here. It'll create a circle at the center of the helix, the helical path, the spiral path. What we actually want is for this circle to be on the path itself. So all we really need to do for that to happen is just add the coordinates of the path itself. So that would just be curve at t, and we just add that to all the calculations we just made. So that will give us a circle on our path. Now, the problem is that we can't just have one circle on the path. We want multiple circles at different points on the path. So one way to do this would be to use a for loop and do the whole calculation 18 different times. But a simpler way to do this would be using the JNP vectorize function, which basically does the same job, except it's a lot easier. So the syntax for that would be jnp.vectorize, and we would pass a function to this. So we would pass our surface function, surf, and it also takes a signature, and the signature for this would look like it'll take one scalar, which will be the time, and then another scalar, which would be theta. There isn't a comma there, and it will give us a vector of 3 dimensions. So that would be the signature. It looks like we missed something here. So the surf function should also take time and theta as inputs. Okay, it looks like we were supposed to have a comma there, so let's put that back there. Now that we have this function, what we want to do is we want to take all the values of time and theta and use their to be able to use their combinations. We want to store all of those values in a separate variable. So that would be s equals, we'll use the surf vec function, and this will take the inputs, all the time values, so, and then all of the theta values. And there we go. Oh, looks like there's an error there too. Okay, it looks like we forgot to use JNP here, so I think that's what caused the issue. So let's do that. Alright, there still seems to be an issue here. Okay, there seems to have been a missing bracket here as well, so that's an issue. Okay, so we have that. Okay, hopefully everything works now. Oh. Okay, let's get rid of that one, and okay, there we go. So everything's working now, so we have that. Let's take a look at what the shape of this vector looks like. So s dot shape. Alright, so what we see right here is that we have 36 different values for the actual function or time value, 18 different values for theta, and 3 would be the x, y, and z values of this, of the actual coordinates. So what we can do now is, if we transpose this function, say t, we get the x, y, z values on the front. So now we can unpack this. So what we can do here is x comma y comma z is equal to s dot t, which means the transpose of the function s, the matrix S. So we can get the x, y, and z values differently. Now, finally, we've pretty much completed the whole thing now. All we really need to do is plot this out. So let's make a section here called graph. Now, it's pretty much the same thing that we usually do. So fig equals make underscore subplots. So we have added a square bracket there. Alright, and what we want to add here is like fig dot add underscore scatter 3D. First, I want to plot the surface lines of the hose. So what we do here is scatter 3D with this x equals. So this would be okay. First of all, we want to plot multiple lines. So what we actually want to do is do a for loop here first. So for I in range. In order to plot the circles first, what we can do is theta, take theta dot size, and put a colon there and indentation. So the x values of theta actually lies on the first part, so that would be I comma colon y equals y, I comma colon, and then z equals z at I comma colon. So those are the x, y, and z values, and of course the mode needs to be lines because we want a line graph. Okay, and once we have all that, let's update the layout. So that would be fig dot update underscore layout, and we'd have width equals 600, height at 600 as well, and then template would be Plotly Dark. So let's see what that looks like. Alright, we almost already have our whole hose ready. Just to make these legends disappear, I will add another argument here. Show legends equals false. Oh, it looks like it's the wrong argument. Let's do show legend. Okay, that's a lot better. The last thing we want to do is probably add those circles in. So it's pretty much the same thing as we did right here. So I'm just going to copy and paste this. Except that this time the size would be for t. And then this would be stored on the second part, I. Right, let's see what that looks like. Oh, it looks like there's a mistake here. Valid syntax. Oh, it looks like we got rid of a square bracket there. Okay. And there we go. So yeah, that's pretty much what we were looking for. So yeah, that's how we plot a 3D hose in MATLAB, in Python.